answer that question, we have to use some logic. So the first thing is, if it's occupying a particular area, if it's here, but it's not there, well, maybe it evolved here, and that's why it's here. Or it evolved someplace else and it migrated right here. Okay? It either evolved here or it came from someplace else and migrated over here. That's logical. And then the counter to that is, if it's not here, well, why not? It evolved someplace else, but it never got here. Or it was once present, but now it's extinct. It either went away or it went extinct in that particular locality. Okay? So those are really common logical deductive reasons for why it's here, but not there. How do you test it? So the first thing we need to do in terms of distribution is to look at our maps. The largest ecological map that you would see an ecologist use is something called the biogeographic region or realm. And there's 6 major biogeographic regions or realms on the planet. So we live in the Nearctic, South America is Neotropical, we have the Palearctic, Ethiopian, the Australasian, and on and on and on. So when you look at them, what defines the boundaries between them? The boundaries between biogeographic regions or realms are defined when species composition changes rapidly over a short spatial scale. So for example, if I look at the Nearctic into the Neotropical, the transition zone is very tight, and it's in Central America. And I'll go from like Chuckawalla lizards and Gila monsters and deer, and all of a sudden I'll start seeing monkeys and parrots, right? And jaguar and things like that over just a couple hundred miles. That's where we shift from one biogeographic region to another. The boundary there is really tight. Why? Because there's a constriction in physical space. When you take a look at something like the Palearctic into the Ethiopian, those transitional bands are much broader because the spatial area is much larger in terms of the area of overlap. Okay? So it's tight where the physical space is constrained. It's much broader where it's not. But again, the distinction is they are defined in terms of boundaries where species composition changes rapidly over short spatial distances. Now, when we take a look at the distribution of things on the planet in terms of organisms, a lot of those biogeographic regions and realms are primarily determined by climate. And this is, again, our communication issue. So what is climate defined as? The average of what? Weather over long periods of time. Weather is simply a short-term atmospheric phenomenon. It's hot today, it's raining today, it's X-humid today, the wind speed is this today. Climate is that weather averaged over very long periods of time. The 2 primary determinants of climate that are important for distribution predominantly, not that the others are not important, but the ones that dominate are how hot it is and how much water there is. Okay, those are the 2 big aspects of climate. So communication here is really important. We talked about this idea of global warming as being a real mistake on our part in terms of communication. Look around the planet right now, and we're not in very good shape. Okay? This is the 4th hottest year in recorded history. It's hot. And it's been hot for a while. And it's going to get hotter. So how do you deal with that? Lots of people are ill-informed, uneducated about it, and resistant to it. Because what happens is, since the scientific background has not been clearly elucidated and described, they fill up the gap with perception, conjecture, and belief. Now, as a scientist, do I really care what you believe? I don't care. What do I care? I care what you understand. That's what I care. All right? However, you have to be able to understand, you have to have factual information and perceive it as fact. So the problem is this idea again. It's this hot, coldest day in June in the middle of July. Global warming is a hoax. And then politics and cultural stuff comes into play for a variety of different reasons to obfuscate and cloud the whole thing up so we do nothing. Is that a good idea? No. While we fiddle, what happens? Rome burns, you know? And that's kind of the idea there. So here's the thing for you, is to educate the population again about what's going on and why it's occurring. I often get in arguments, and you might too as a biologist or as a scientist, about global warming. And so the first thing, if someone comes up to you and wants to argue about it, the first thing you should ask them is, what is the difference between climate and weather? Before you get anywhere, talk about anything, ask the question. And so if they can explain it, great. You can have an educated conversation back and forth. But if they can't tell you, then what? You have a couple options. What are your options? What's that? Yeah, you can just stop arguing and just go, forget it, not worth it, walk away. Right? You have a belief system that has nothing to do with the facts. And so you can walk away. What else can you do? You can educate them on the facts. Maybe you just give them a big slap. Then you educate them, or walk away, whatever you do. All right? But it's really important, so that's a good problem. So climate then dictates distribution of organisms. And so how is climate generated? That's the next question. So climate is generated by differences in solar radiation as we move around the sun. And that difference in solar radiation is going to drive both atmospheric and oceanic circulation systems. So here's the thing. Our planet sits like this and it spins around its axis. It's hot when? What part of the 24-hour cycle? In the daytime when we face the sun. It gets cooler when? And night when we're away from the sun. Well, that's pretty basic. But we also have seasonal cycles. Seasonality is due to the tilt of the Earth. What's the Earth set at tilt? 23.5. So it kind of sits off to the side like this. If it was straight up and down, would there be any seasonality on the planet? Every place on the globe, depending on where it would be the same on an annual cycle. So it would be kind of an average between our summer and winter all the time, right? Down the tropics would be hot all the time. Down at the poles would be cold all the time. There really wouldn't be 6 months of hot, 6 months of cold. It'd be the same. So this changes everything because we zip around the sun like this at an angle. And so what that does is it's going to give changes in the amount of sunlight that's hitting the planet at any one point in time. So how does it basically work? Well, the tropics are a lot hotter than the poles. So when you look at it, that's actually a typo that I just saw over there. See where it says acute? That should be obtuse, so change that. I just noticed that. All right? So that is not acute, that should be obtuse. All right, let's walk through it. Let's take a look at the angles of attack. What's the angle of attack at the equator for the sunlight hits the planet? What is that? That's a right angle. So that means that there's a tremendous amount of solar radiation hitting the equator dead on. And that means there's a lot of energy. But what about the area that it covers? Is it very big? No. That's really small. So it's a limited area with the sunlight hitting it directly. That means a lot of that energy is loaded right on into the water and right on into the atmosphere at high intensity. But look as we get towards the poles. The angle's no longer right. What happens to it? It opens up, and now it's an obtuse angle. It's got more area. So when you look at it, the sunlight is penetrating through longer areas of atmosphere across that angle. And what about the area of the planet that it's covering? Is it greater or smaller or the same as at the equator? It's a lot bigger. So that means I have the same amount of radiant energy, but it's spread out over a bigger area, and it's going through atmosphere for longer. So that means it can be scattered, it can be reflected, and it can be absorbed, and that means less energy delivered at the poles. So therefore they're going to be what? Hotter, the same, or cooler than the equator? A lot cooler. So that's why we have all kinds of energy in terms of heat at the equator, and not so much up at the poles. So what this is going to drive then is our global air circulation patterns on the planet. And so how does it basically work? Where's the sunlight hitting the planet the most intensely? At the equator. What happens to air as it gets hot? It rises. That air up there is really hot compared to actually down here where it's still pretty stifling, right? So that air starts to rise. Now look at the equator. Is it mostly land or water? It's mostly water. So what happens is all that energy is evaporating the water on the oceans and it's liberated into the atmosphere and it starts to rise. So there's a lot of water in that atmosphere. As it rises, what happens to the temperature of the air? Does it go hot, stay the same, or cool? It cools down tremendously because at altitude you're getting into space, it starts to cool. Now, as it cools, the atmospheric molecules slow down. So what happens to the water in them? It drops out as precipitation because they're slowing down. So at the equator, the conditions are hot, but they're also what?
Wet.
They're wet. If I have hot and wet climate, what kind of biome will I find there? A tropical rainforest. And take a look at the map. See the dark green right across the equator? That's tropical rainforest. It's hot and wet. Now, that's if I just go straight up. But it's hot in the middle and cold at the top and cold at the bottom. So where's air going to want to go once it rises up? It's going to go where? Towards the poles. It's going to go from hot to cold because there's a high concentration of heat at the equator and a low concentration at the poles. What's that movement then called? High to low. That's just basic diffusion. All right? So that hot air wants to go north and south. It will start to progress north and south. However, what will happen is rising air creates what kind of pressure? You know? So if something is lifting off, what's the pressure underneath as this goes up? It's low. So I'm releasing the pressure. It's lifting. So there's low pressure here. That's like empty space. It has to be filled. Gas has to flow into there, right? So where does it flow? Well, it flows from the north and the south along the ground towards the equator to fill the gap. That creates another pressure zone at 30 north and 30 south where the air then drops to fill the void. As that air drops to fill the void, it's going north and south to equilibrate the temperature, but now it starts to drop to equilibrate because of the pressure. But as the air falls, is it going to have a lot of moisture? No, because I used it up all where? It's shed it all at the equator. Now, as it goes from high altitude towards the ground, is it going to get colder or hotter? It's going to get hotter. It starts to get pressed compressionally, right? You ever filled an air tank like an aqua lung? That air gets hot in there, right? You're pressing on it. And so that air is hot and that air is dry. Well, what kind of biome are you going to get then? A desert. That's exactly right. So 30 north and 30 south latitudes, you get deserts. The same exact process, that loop is called a Hadley cell. You don't need to worry about that. But it's this kind of cell that's generated from diffusive properties of high to low concentration of heat and pressure differentials of high to low. Okay? Now, the next cycle is going to occur at 60 north and 60 south latitudes. The same basic cycle that happened at the equator happens there. The air is not hot, however. What's the air around, like, say, Oregon, Northern California? Is it cold?
No.
It's not cold. It's what? It's kind of moderate cool, right? It's cool air. There's a lot of water up there again. And so what happens is moist, cool air rises. As it rises, what's it going to shed as it slows down? Water, and it rains again. So at 60 north and 60 south, you have cool air, but it's raining. What kind of biomes do you get? You get temperate rainforest. And that's, think of like the redwood forest, okay? Temperate rainforest. Same basic idea. It's going to want to go north and south because it's colder at the poles. However, there's pressure differentials now. It wants to flow back to fill the low pressure zone, and it loops again. So at the poles, it starts to fall again. It's not going to get hot compressionally because it's so cold at the poles anyway. But is it going to be wet?
No.
No, because all the moisture is shed where? At 60 north and 60 south. So it falls as cold, but what? Dry. So what do you get at the poles? A polar desert. They're deserts. They're just cold deserts. Okay? That explains all the climatic bands on the planet. At the equator, it's wet and it's hot. Rainforest. At 30 north and 30 south, it's hot and it's dry. Deserts. At 60 north and 60 south, it's cool and wet. Temperate rainforest. At the poles, it's cold and dry, polar deserts. It also explains what's in between. What's in between a desert and in between the rainforest tropical? It's mid in terms of heat and it's mid in terms of the water. What are you going to get there? Grasslands and savanna. Okay? What's between the poles and the temperate rainforest? You're going to get tundra, right? Between cold and cool, and between wet and dry. So that explains all the different patterns. That's how distribution is determined on the planet via the climate. All right, so that's the basic idea. Temperate rainforest, finally polar deserts. All right, climate determines the distribution of biomes. What's a biome? Terrestrially, it's defined by what the dominant vegetation type is. Aquatically, it's determined by what's the physical and chemical construct of the water. All right? So climate's going to dictate the distribution of the biomes. Where do you find a tropical rainforest? So wherever it's hot and wet, I'll find a tropical rainforest. I find it in the same place in Australia as I do in Africa, as I do in South America, and the conditions are quite the same. Now here's the trick, however. The plants look the same. Big, giant, tall trees, big, massive leaves. They're all doing the same thing in the same kind of places. However, when I look at them from a species level, they don't look anything alike. The species that I find in tropical Australian rainforest have nothing to do with the species I find in a tropical African rainforest or a South American rainforest. They're totally different. Functionally similar, right? Taxonomically dissimilar. They don't share evolutionary descent in many cases. Sometimes they do, but in many cases they don't. So I'm right back to my original question. I can tell you what kind of biome you're going to find, but I can't tell you why one species is there and another one is here, based strictly on the climate. All right? So large-scale distribution patterns can be predicted by climate, primarily water and temperature. But small scale, I don't know. I don't know why that species is here and that species isn't there. So I need a more finely resolved tool in order to explain that, right? Why does a species not occur? What limits its distribution? All right. So climate is a neat thing. In terms of seasonality, just real quick, it's super hot right now because it's our summer. So here's the sun, and we spin around it, right? So right now, where are we? What hemisphere? North hemisphere. Where's the tilt look like? Is it like this, or like this? This is like this, all right? So here's our summer. The northern hemisphere is receiving the most intense sunlight. That's why we're hottest. What's it called? Maybe last month, June 21st. That was the summer what? What does that mean? That's the longest day in the year for us in the northern hemisphere. But as we move around, pretty soon we're going to be here in fall. Where's the sunlight hitting now? Dead center on the equator. What's that called? The vernal equinox. But then it's going to be over here. What's that going to be? That's our winter solstice, where we're farthest away from the sun and South America is getting blasted. And then we're going to be back here. What's here? I screwed it up. It's the summer solstice, autumnal equinox, right? Winter solstice, and then this is the vernal or the spring equinox. That's how it works. That's why we're getting our seasons. Okay? Pretty neat, actually, how we spin around. And then it gets even more twisted up because we're rotating along the way. Does our planet get hot and cold naturally? Is global warming and global cooling a natural phenomenon? Absolutely. 100%. It's not a perfect spin. We warble. Sometimes we warble closer to the sun. Sometimes we're farther away. When we're close, we get hot. When we're farther away, we get cool. Geologic activity has a lot to do with it. Sometimes the planet's real active, pumps a tremendous amount of junk in the atmosphere, makes it thicker, we get hot. Sometimes when we're nice and stable, atmosphere gets thinner, we get cool. Right now, we're on a natural ascent of heat. The problem is, since 1847 or 45, we've deviated off the natural liner and straight ascent. Why? Because that correlates with the burning of fossil fuels at the start of the Industrial Revolution, and it hasn't let up. So we should have been starting to crest, but we're not. We're still climbing. So we're having a direct influence on that natural long-scale phenomenon. All right. So back to our original question. Why is the species not here, but it's over there? Well, we have a tool, and that's a simple transplant experiment. If I want to know why it's here but not there, well, I'll take it from here and put it over there and see what happens. All right, so that's a basic transplant experiment. It is one of the major conceptual and experimental techniques that an ecologist utilizes to determine distribution of organisms. If I take it from here and I put it over here, a transplant has to be generated by two events. First, the organism must survive, and then it must be able to reproduce in the new habitat for a transplant to be successful. Survival does not mean that the transplant is successful. It must reproduce as well in the new habitat. Okay? Those are the two diagnostic characteristics of a successful transplant. And then you've got to follow it through at least one generation. So what is the outcome then? So if my transplant is successful, well, what does that mean? It means that the potential range of a species is actually larger than its actual range. It's bigger than what it actually is. And if a transplant is unsuccessful, that means that the potential range is the same as the actual range. It's no larger. Those are the two logical outcomes. All right, well, let's look at these kinds of transplants and what could potentially be limiting why it's here but not there. And so the first one is, well, maybe it just can't get there. It can't get from here to there. If I do a transplant and it's successful, well, why isn't it there? Well, maybe it can't get there. So what's that animal on the left? The fuzzy one. Can I recognize it? That's a kiwi. That's a bird. Can it fly? No. When it flies, it's a bird. Where is it found? New Zealand. Now here's the thing. I can transport kiwi to islands that are almost identical in habitat, and they will do fine in many cases. Well, why aren't they there? Because they can't get there because they can't fly. That's the only reason. So they could potentially be quite successful, but they're not. So dispersal limits their distribution. Another reason it might be here but not there is they choose not to go there. I can get there, but I choose not to go there for whatever reason. Maybe there's predators or competitors there, I don't want to be there. Or I look at it, but I simply don't recognize it as a viable place to go. I make a mistake. I can't be there, so I don't go there. So that would be a form of habitat selection. So if the transplant's unsuccessful, well, why might it have failed? Maybe I take one species and I plunk it over there and it instantly dies. And the reason is because there's a bunch of predators. I take the kiwi and I put it down in an identical habitat, but the difference is there's ground-dwelling snakes in that habitat and not in New Zealand. So I stick them over there, and what happens to the kiwi? They get blasted and they can't rear any young, because as soon as the young come up, they get consumed by the snakes. So that will limit their distribution, even though the abiotic conditions of the habitat are okay. The biotic conditions are not. So maybe there's a disease over there that's not over there. Maybe there's another bird that's already on the ground over there, taking up all the occupied habitat. There's no room for them to competitively succeed. So that's a reason why it might fail. Interdependent species are really important too. So I take one species that's doing fine here, I plunk it down in the new habitat, and it dies. I'm like, everything looks fine. Why did it die? Well, maybe because I didn't bring its symbiotic relationship with it. Prime example would be pine trees. So there's certain northern pines here that we have that we utilize as ornamental trees, and we ship them all over the place. Have you ever noticed when trees come packed in, they come packed in soil, right? Well, that takes a lot to ship because you got to ship all that weight. It would be much cheaper just to ship the tree and its roots without all that soil. But if you do that with these pine trees and you stick them in the ground, they will die within a matter of weeks. But if I transplant them with their soil, they'll do fine and live 100 years. What was the difference? It wasn't the soil itself, because the soils look identical, but it was something.
Was it fungus?
It was a fungus associated with the soil and the roots. So pine trees are often found in habitats where the nutrient levels are real low. And so what happens is they have these mycorrhizal fungi assemblages that increase the surface area of their roots and also help them liberate compounds and nutrients from soil that would be very difficult to get on their own. And they're able to grab more nutrients, and that helps the plant survive. So if I take them with their soil, which includes their fungus, that's the symbiote, they do great, and they work fine. If I just take the pine tree, it dies because its symbiote is not transplanted as well. That's often why transplants fail. Or it can be something as simple as there's not enough water over there. It's too hot. There's not enough light. Simple abiotic, chemical, or physical conditions might limit it. So let's look at some experiments in terms of dispersal. So remember, dispersal is just a movement from one place to another. The vast majority of living things are mobile to some degree. But mobile is completely relative to an organism. So for us, marching around on campus is no big deal. To get from one side of the Rocky Mountains to the other with no technology, is that a big deal? Yeah, people died all the time before there was modern technology. They ended up eating each other in the passes and things, right? That's not easy. But for birds, isn't that big a deal? No, they fly right over through the passes at certain times of year. Not a big deal at all. So bacteria. Bacteria in this seat to the bacteria in this seat just left alone. Is that a barrier? That's a universe away, right? The only way they can get from here to there is what? If we moved them somehow by getting on you and you walked over there and sat down or something like that, right? So again, completely relative to the organism itself. Geographic barriers are quite common in nature. So here's a nice example. This is in the Southern California intertidal community. So here's Santa Barbara, this is the south coast, and then we have the central coast of California. The cutoff is Point Conception. That's where the landmass goes from a north-south orientation to an east-west orientation. Then it goes south along our coastline, and then at Ventura, and then it goes north-south again. All right, so it does this weird kind of Z shape. So what you see when you do observations is, above Point Conception in Central California, there's a particular kind of barnacle on the rock that's found all over the place, and it's Balanus caryosis. Barnacles basically are little crustaceans. They have a little calcareous test that looks like a volcano. And if you crack that shell open, what you'll see is they look like an upside-down shrimp. And they fan their legs to filter feed the water. So they're sessile. What does that mean? They're locked into place. They're glued in as an adult. But they do have a motile stage, and it's the larva. And that's the one that moves around from place to place in water currents. They can't swim or anything very well, but the water currents move them all over the place. So they're shed, they move, and they find new habitat. So all up and down the central coast you find this barnacle. But notice along the south coast in Santa Barbara here, none of it. Nowhere to be found. Literally over the span of a couple miles it disappears. And it's no longer there. What's your question as an ecologist? Why? Why there, but not there? Okay, why there, but not here? That basic ecological question again. All right. So, do you have a tool to test that?
Yes.
What is it? A transplant experiment. That's exactly right. You have a tool to test it. So, here's our hypothesis to explain why it's here, but not, or why it's there, but not here. Well, maybe they get here, but the conditions are really terrible. It's too hot. Maybe there's not enough oxygen. Maybe there's not enough of what they eat. For whatever reason, is the conditions are poor here in Santa Barbara, and they die. So the abiotic or the biotic conditions are poor and do not allow them for successful survival or reproduction. Or there's something about Point Conception that might act as a barrier. Now, I don't see that myself because I'm a human being. And it looks like the water's completely contiguous. Why not just wrap right around Point Conception and come on in? Right? I don't see any real physical barrier, but I'm not a barnacle. Okay? So, what's our test? I'm going to take it from there, and I'm going to move it there, and I'm going to see if it does what? Survive and reproduce. That's exactly right. And so, this experiment was actually done by a graduate student right here at UCSB, and that's what they did. So, they did a transplant experiment. They went up to Santa Cruz. They grabbed the barnacles off the rocks. They grabbed the rock itself, stuck it in buckets in the back of their truck, and then drove it from Santa Cruz down to Santa Barbara and stuck the rocks right into the intertidal. And then they monitored to see if it would survive and reproduce. Okay? That was the idea. Now, here's the trick on this. If I transplant them and they die, am I going to accept or reject hypothesis 1 that the conditions are poor? I'd accept it. However, I can only accept that hypothesis if I have a what in terms of my experiment. If I just move them down here, plunk them in, and they die, do I have high confidence that the conditions were poor? What am I missing? A control for what? The control for the transplant itself. So if I'm a little barnacle and you rip me out of the ocean, throw me in a bucket, and make me drive for 6 hours and then throw me back down someplace else, that can be pretty traumatic, right? What if I was to come into your house, rip the roof off, grab you, throw you in a cage, rock you around for 6 or 7 hours, rip you out, and throw you in another house a million miles away. And then said, act naturally. Go reproduce for me, please. You gonna do that? Probably not. You might have some issues. And so living things are really susceptible to these kind of manipulations. So we have to control for that. So how can I control for the transplant itself to make sure that wasn't responsible for the death? It took 6 hours from there to there. What do I have to do? I drive 6 hours, but what do I do with the barnacles I have in the truck? I put them back where I got them. And that's exactly what they did. So they took the barnacles, they drove halfway down from Santa Cruz, they turned around, drove right back, and stuck them right back in the ocean. Those barnacles lived fine. So what does that tell you about the transplant? It's fine. The transplant itself is not responsible for the death. So that's a nice control. Without that control, the experimental results are meaningless. They're just guesswork. They're conjecture. All right, so that control is halfway down, halfway back. All right, here's the results. The barnacles live both in the controls and in the transplants. What does that tell you immediately about the habitat?
Habitable.
What's that?
Habitable.
It's completely habitable. It's not abiotic, right? There's nothing, temperature, chemical, whatever, that precludes them from existing here. If you get them here, they're going to survive and reproduce. So what does that leave as our alternative hypothesis? There's what? No, because we're testing for all that stuff with the transplant. So what's left? What's our alternative hypothesis? There's a barrier. So I look and I say, well, what the hell is the barrier? So if I go and measure it, the first thing I see is, remember that the barnacles themselves, they're motile, but they're dependent on what to get around? Currents. Now when I look at the currents off the coast, what I see is the Alaskan current zips down past Point Conception, but doesn't bend in. It whips out and then goes around the islands on the outside. So that means if I haven't settled out and got to the bottom and found a place to live, what happens to me if I'm a barnacle? Out to the open ocean I go, and then I do what? I die, because there's nowhere to settle at. That's why they're not here. So it is a physical barrier to their habitation of this coast. All right? So again, hypothesis 1 is false, hypothesis 2 is correct. It's a barrier. Next time we meet, we'll carry on. Have a good day.